The universe is pulling itself apart in ways that reveal something profound about the nature of reality itself. What makes this expansion so fascinating is not just that it happens, but what it shows us about our place in cosmic history and the ultimate fate of everything we can see. The expanding universe acts like a massive time machine, allowing us to peer into the past and glimpse the future simultaneously. And what we discover challenges everything we thought we knew about permanence and possibility. One of the most remarkable things the expanding universe shows us is that we live in a privileged moment in cosmic time. Right now, in this particular epoch, we can still observe evidence of the Big Bang. We can still see distant galaxies scattered across the sky. We can still detect the cosmic microwave background radiation, that faint echo of the universe's birth. But this window of observability is temporary. In about 1 trillion years, the cosmic microwave background will have redshifted so far toward longer wavelengths that it will become essentially undetectable. Future civilizations arising in that distant era will look out at a universe that appears to contain only their own galaxy, surrounded by infinite darkness. They will have no way to discover the Big Bang, no way to understand cosmic expansion, no way to know that billions of other galaxies once filled the sky. The evidence of our cosmic origins will have literally stretched itself out of existence. The Planck satellite mapped the cosmic microwave background with extraordinary precision, revealing the universe's composition in unprecedented detail. What it showed us is that ordinary matter, the stuff that makes up stars and planets and people, comprises only about 5% of the universe's total energy density. Dark matter accounts for about 27%, but the dominant component, making up roughly 68%, is dark energy. This dark energy is not just present, it is active, and it is winning a cosmic tug-of-war against gravity. That 68% is not a static figure either. As the universe expands, the density of matter and dark matter decreases, but dark energy remains constant. This means that over time, dark energy's proportion of the universe's total energy actually increases, making cosmic acceleration more and more dominant. What the expanding universe shows us about dark energy is perhaps the most unsettling discovery in modern cosmology. The Hubble Space Telescope's observations of Type 1a supernovae in the 1990s revealed something that shocked the scientific community. These supernovae, which serve as cosmic distance markers because they always explode with the same brightness, appeared dimmer than they should have been at certain distances. This dimness meant they were farther away than calculations predicted. Distant galaxies were not just moving away from us, they were accelerating. The Supernova Cosmology Project and the High-Z Supernova Search Team independently confirmed this finding, and the discovery earned the 2011 Nobel Prize in Physics. But for anyone contemplating the long-term future of the cosmos, it was perhaps the most troubling news possible. The current expansion rate, called the Hubble constant, sits at approximately 70 kilometers per second per megaparsec. A megaparsec equals 3.26 million light-years. This means that for every 3.26 million light-years of distance, galaxies recede an additional 70 kilometers per second faster. The Andromeda galaxy, positioned about 2.5 million light-years away, should technically be receding at roughly 54 kilometers per second due to expansion alone. It is not receding because its local motion toward us, driven by mutual gravitational attraction, overcomes the expansion effect. But this only works because Andromeda is so relatively close. For more distant galaxies, expansion wins. The Dark Energy Survey, using the Blanco telescope in Chile, has mapped millions of galaxies to trace this acceleration with remarkable precision. The results show unequivocally that dark energy dominates the universe's dynamics, and that acceleration has been increasing for approximately 5 billion years. This acceleration has profound implications. It means that every moment we wait, every second that passes, our potential cosmic destinations race away faster. Galaxies currently at the edge of our observable universe are already receding faster than light. We can still see them because we observe light they emitted billions of years ago when they were closer. But any light they emit now will never reach us. They have crossed what astronomers call the cosmic event horizon. The cosmic event horizon currently sits at approximately 16 billion light-years away. Galaxies beyond this distance are already unreachable. They recede faster than light, and nothing we could ever send, even traveling at light speed, would catch them. This horizon is not fixed. It is actually shrinking in what physicists call co-moving coordinates. This means that fewer and fewer galaxies remain within our potential reach as time passes. Every year, approximately 20,000 stars pass beyond this horizon, lost to us forever. The expanding universe is not just separating us from distant objects. It is actively and continuously reducing the portion of the cosmos we could ever hope to access or influence. The Sloan Digital Sky Survey has created three-dimensional maps of millions of galaxies, revealing how they distribute themselves in vast cosmic webs and voids. These maps also contain the expansion history of the universe, written in the positioning of galaxies at different distances. Looking at galaxies at various distances means looking at different times in the past, because light takes time to travel. By analyzing how galaxy distribution changes with distance, astronomers can see how the expansion rate has evolved. The verdict from all these measurements remains consistent. Acceleration began about 5 billion years ago and has been increasing steadily ever since. There is no sign of it slowing down. There is no indication it will reverse. The universe is committed to pulling itself apart with ever-increasing vigor. The Atacama Cosmology Telescope and the South Pole Telescope have measured tiny variations in the cosmic microwave background that reveal even more about expansion history. These instruments detect temperature fluctuations of only a few millionths of a degree. Yet these minuscule variations contain vast amounts of information about how the universe has evolved. Combined with supernova observations and galaxy surveys, all measurements point to the same inescapable conclusion. Dark energy is real, acceleration is happening, and cosmic isolation is our ultimate destiny. What makes this particularly profound is what the expanding universe shows us about time itself. The universe has a peculiar property, where looking farther out in space means looking farther back in time. When we observe a galaxy 10 billion light-years away, we see it as it was 10 billion years ago. The light from that galaxy has been traveling through expanding space for 10 billion years, and during that journey, space has stretched the light itself. This stretching shows up as redshift, where light waves lengthen toward the red end of the spectrum. The most distant galaxies are redshifted so severely that their visible light is stretched all the way into infrared wavelengths. This cosmic redshift provides a direct measure of how much space has expanded since the light was emitted. The James Webb Space Telescope, with its powerful infrared capabilities, can detect galaxies as they appeared more than 13 billion years ago, when the universe was young and compact. These early galaxies were closer together, interacting and merging frequently. That cosmic neighborhood is gone forever, stretched apart by billions of years of expansion. We observe the universe's youth, knowing we live in its isolating middle age. This creates a strange temporal perspective. We can see the past in extraordinary detail, watching galaxies as they were billions of years ago. But we can never visit those galaxies as they are now. By the time we could possibly reach them, if we ever could, billions more years would have passed, and they would be entirely different. The baryon oscillation spectroscopic survey has traced how sound waves in the early universe created a characteristic scale in galaxy clustering. In the first few 100,000 years after the Big Bang, pressure waves rippled through the hot plasma filling space. These waves, called baryon acoustic oscillations, left an imprint on how matter distributed itself. Even today, billions of years later, galaxies show a subtle preference for certain separation distances that echo those ancient sound waves. By measuring how this characteristic scale appears stretched at different cosmic distances, astronomers can trace the expansion history with remarkable accuracy and project it forward into the future. Every measurement confirms the same unsettling picture. The universe is pulling itself apart, and there is nothing anyone can do to stop it. What does all this expansion show us about the composition of the universe? The illustrious simulation, one of the most sophisticated computer models of cosmic evolution ever created, demonstrates how large-scale structure forms and evolves. Galaxies are currently arranged in a cosmic web of filaments and clusters, with enormous voids between them. This web forms because dark matter creates gravitational scaffolding that guides ordinary matter into dense regions. But dark energy works against this structure. Over time, dark energy will gradually tear the cosmic web apart. Clusters will disconnect from each other. Then galaxies within clusters will drift apart. Eventually, only gravitationally bound groups will survive as isolated islands in an ever-expanding sea of emptiness. Future projections are sobering. In approximately 100 billion years, all galaxies outside our local group will have passed beyond the cosmic event horizon. The local group itself, consisting of the Milky Way, Andromeda, Triangulum, and dozens of smaller galaxies, will merge into one giant elliptical galaxy. This merged galaxy will float alone in an empty, dark universe, with no other galaxies visible in any direction. Any civilization arising in that future epoch will have no evidence that other galaxies ever existed. They will observe a universe that appears to consist solely of their own galaxy surrounded by absolute darkness. The anthropic principle takes on new meaning in this context. We exist at a special time when the universe's history remains visible, when other galaxies still dot the sky, when the evidence for our cosmic story remains accessible. Recent observations by the Dark Energy Spectroscopic Instrument reveal the universe's large-scale structure in unprecedented detail. Vast filaments of galaxies separate even vaster voids. These voids, some spanning hundreds of millions of light years, preview our future. They are regions where cosmic expansion has won so completely that few galaxies remain. In the far future, such voids will encompass everything beyond our gravitational island. The Boötes supervoid, spanning 330 million light-years, shows us what most of the universe will eventually become. This nearly empty region contains far fewer galaxies compared to surrounding space. In the distant future, such voids will be all that remains, with island galaxies like ours separated by billions, then trillions of light-years of nothingness. The European Space Agency's Euclid mission, launched in 2023, is designed specifically to study dark energy through observations of billions of galaxies. Its measurements will refine our understanding of cosmic acceleration, but every refinement so far has only confirmed the basic picture. The universe is pulling itself apart, and the process is accelerating. Euclid will map how galaxies cluster and how that clustering evolves over cosmic time, providing even more precise measurements of dark energy's properties. Yet all signs suggest these measurements will simply confirm what we already know with greater precision, rather than revealing any escape from our isolation. What the expanding universe shows us about our cosmic neighborhood is particularly interesting. The local group, our collection of gravitationally bound galaxies, will survive the expansion. These galaxies are close enough and their mutual gravity strong enough that dark energy cannot pull them apart. But this survival comes with transformation. When the Milky Way and Andromeda collide in approximately 4.5 billion years, the night sky will be spectacular for millions of years as the two galaxies interpenetrate and merge. Stars will not actually collide because space between stars is so vast, but gravitational interactions will fling stars into new orbits, trigger waves of star formation, and eventually settle into a single aging elliptical galaxy with little new star formation occurring. The expansion also shows us something profound about information and causality. The integrated Sachs-Wolf effect, observed by comparing the cosmic microwave background to galaxy surveys, confirms that space itself is stretching between galaxies. The baryon oscillation spectroscopic survey and dark energy survey have mapped this expansion in exquisite detail. Galaxies more than about 16 billion light-years away are receding faster than light. This does not violate relativity, because they are not moving through space faster than light. Rather, space itself is expanding between us and them. But the effect is the same. We are causally disconnected from these regions. No signal we send can ever reach them. No information from them can ever reach us beyond what they emitted in the past. This reveals something fundamental about the universe's information structure. The holographic principle, developed by physicists Gerard 't Hooft and Leonard Susskind, suggests that all information in any region of space can be encoded on its boundary. This deep connection between information, entropy, and geometry might explain fundamental limits on cosmic connectivity. As the universe expands and regions become causally disconnected, information becomes distributed across boundaries that we can never cross. The expanding universe is not just separating matter and energy, it is fragmenting information itself. The cosmic microwave background, that faint echo of the Big Bang, currently bathes us in microwave radiation with a temperature of approximately 2.7 degrees above absolute zero. This radiation has been cooling as the universe expands. In the distant past, this radiation was much hotter. In the far future, it will be much colder. Eventually, it will cool so much and redshift so far that it becomes undetectable. When that happens, which will occur in roughly 1 trillion years, future observers will have lost their best evidence for the Big Bang. The expanding universe will have literally erased its own origin story from the observable cosmos. What this expansion shows us about dark energy remains one of physics's greatest mysteries. We can measure its effects with remarkable precision. We can quantify how much of it exists. We can track how it has influenced cosmic history. But we do not understand what it is. The simplest explanation is vacuum energy, the idea that empty space itself possesses energy. Quantum field theory predicts that even empty space should have energy from virtual particles constantly popping into and out of existence. However, when physicists calculate how much vacuum energy should exist, they get a number that is roughly 10 to the power of 120 times larger than what we actually observe. This is arguably the worst prediction in the history of science. Something is clearly missing from our understanding. Alternative explanations for dark energy include quintessence, a hypothetical field that permeates space and whose energy density can change over time. Unlike vacuum energy, which remains constant, quintessence could potentially vary, leading to different expansion rates at different cosmic epochs. Some theories propose modifications to general relativity itself, suggesting that gravity behaves differently on cosmic scales than Einstein's equations predict. Others invoke extra dimensions of space that affect how gravity spreads over large distances. Yet none of these alternatives have gained widespread acceptance because they all require additional assumptions without providing better matches to observations than the simple cosmological constant model of dark energy. The expanding universe also reveals fascinating details about cosmic history through what astronomers call the cosmic distance ladder. This ladder consists of overlapping measurement techniques, each valid over certain distance ranges. For nearby stars, we use parallax, observing how their apparent positions shift as Earth orbits the Sun. For more distant stars, we use variable stars called Cepheids, whose brightness varies in predictable ways related to their actual luminosity. By comparing apparent and actual brightness, we determine distance. For still more distant objects, we use Type 1a supernovae as standardized candles. Each rung of this ladder must be carefully calibrated against the previous rung, and any errors propagate upward. The tension in Hubble, constant measurements between different techniques, might indicate that our distance ladder needs refinement or that our cosmological models require adjustment. What makes the expansion particularly interesting is how it affects the light we receive from distant sources. As space expands, it stretches photons traveling through it. This stretching increases the photons' wavelengths, shifting them toward redder colors. The amount of redshift directly measures how much the universe has expanded since the light was emitted. A galaxy with a redshift of 1 has had its light wavelength doubled, meaning the universe has expanded by a factor of 2 since that light began its journey. A galaxy with a redshift of 2 has had its light wavelength tripled. The highest redshift galaxies observed so far have redshifts above 10, meaning the universe has expanded more than tenfold since their light began traveling toward us. This redshift also affects the energy we receive. Photons lose energy as they stretch. A distant galaxy emitting primarily an ultraviolet light will have that light redshifted into visible wavelengths by the time it reaches us. An extremely distant galaxy emitting visible light will have it redshifted into infrared. This is why infrared telescopes like the James Webb Space Telescope are so crucial for observing the most distant objects. They can detect light that has been so severely redshifted that it has moved entirely out of the visible spectrum into the infrared domain. The expansion rate has not been constant throughout cosmic history. In the very early universe, during the first fraction of a second after the Big Bang, the universe underwent an episode of exponential expansion called cosmic inflation. During inflation, the universe expanded faster than the speed of light, growing from perhaps the size of a proton to something at least as large as a grapefruit in a tiny fraction of a second. This rapid expansion solved several problems in cosmology, such as why the cosmic microwave background has nearly the same temperature in all directions, despite regions that should never have been in causal contact. Inflation stretched quantum fluctuations to cosmic scales, creating the seeds from which all structure eventually grew. After inflation ended, expansion continued, but decelerated for billions of years. Gravity worked to slow the expansion as matter attracted other matter. This deceleration era lasted until about 5 billion years ago. Then, as the universe expanded and matter became more spread out, dark energy began to dominate. Dark energy does not dilute as the universe expands because it is a property of space itself. More space means more dark energy, while the same matter gets spread thinner. Once dark energy became dominant, expansion began accelerating. and it has been accelerating ever since. We live in this acceleration epoch. Understanding the expansion history allows cosmologists to age-date the universe with remarkable precision. By measuring the current expansion rate and working backward, accounting for how that rate has changed over time, we can calculate when the expansion began. Multiple independent methods converge on an age of approximately 13.8 billion years since the Big Bang. This age is corroborated by other measurements, such as the ages of the oldest star clusters and the abundances of radioactive elements. The consistency between these different approaches gives us confidence that we understand the universe's basic timeline. The expanding universe also shows us something profound about cosmic geometry. General relativity allows for three possible shapes for space itself. It could be positively curved like the surface of a sphere, negatively curved like a saddle, or flat like an infinite plane. The cosmic microwave background measurements have determined with exquisite precision that the universe is remarkably flat. It is so flat that if it has any curvature at all, that curvature is less than 1%. This flatness is another puzzle. In most models, the universe should naturally curve one way or another as it expands. Maintaining flatness requires a delicate balance between the expansion rate and the total energy density. Cosmic inflation provides one explanation for this flatness. By expanding the universe by such an enormous factor, inflation stretched out any curvature that might have existed initially, leaving us with an effectively flat cosmos. What the expansion reveals about matter distribution is equally fascinating. The Sloan Digital Sky Survey and similar projects have mapped millions of galaxies, revealing that they are not randomly scattered but arranged in intricate patterns. These patterns form a cosmic web of filaments, walls, and voids. The filaments are long chains of galaxies stretching across hundreds of millions of light years. The walls are planar structures where multiple filaments intersect. The voids are enormous regions containing very few galaxies. This structure emerged from tiny density variations present in the very early universe. Regions that were slightly denser than average had slightly stronger gravity, pulling in more matter. As the universe expanded, these density variations grew through gravitational amplification, eventually forming the galaxy clusters and filaments we see today. The expansion also affects how we observe galaxy evolution. Because looking farther away means looking further back in time, we can observe how galaxies have changed over cosmic history. Distant galaxies, seen as they were billions of years ago, tend to be smaller, bluer, and more chaotic than nearby galaxies. They have higher rates of star formation and more frequent collisions. As the universe expanded and galaxies evolved, many underwent major mergers, forming the large elliptical galaxies we see nearby today. Others, like our Milky Way, avoided major collisions and evolved more gradually through gas accretion and minor mergers. The expanding universe has, in a sense, preserved this evolutionary history for us by allowing us to observe galaxies at many different epochs. The expansion shows us that the universe has no center and no edge, at least not in any conventional sense. Every observer, regardless of their location, sees galaxies receding in all directions. This might seem paradoxical, but it makes sense when we understand that space itself is expanding. Imagine dots drawn on the surface of an inflating balloon. As the balloon inflates, every dot moves away from every other dot. No dot is at the center of the expansion. From the perspective of any dot, all other dots are receding. The universe works the same way, except in 3 dimensions rather than 2. This means that if there are observers in distant galaxies, they see the same thing we see. Galaxies receding in all directions, with the most distant ones moving fastest. This property of uniform expansion also ensures that there is no cosmic center that we are moving away from. We are not at the edge of the universe expanding outward into empty space. Rather, space itself is expanding everywhere simultaneously. Every cubic meter of space is getting larger, increasing the distance between any objects that are not gravitationally bound together. This happens at all locations throughout the entire cosmos, creating the impression of universal recession without requiring any special location or direction. The expanding universe presents challenges for certain types of observations. As objects recede, they become fainter for two reasons. First, their light is redshifted, reducing the energy of each photon. Second, the expansion of space means that photons arrive less frequently, reducing the flux we receive. These effects combine to make distant objects extremely difficult to observe. The most distant galaxies ever detected required many hours of telescope time to accumulate enough photons to form an image. Future telescopes will need to be even more sensitive to detect galaxies at greater distances, but there are fundamental limits. Beyond a certain distance, galaxies have receded so far, and their light has been so severely redshifted and diluted that detection becomes impossible with any conceivable technology. What the expansion shows about the early universe is particularly revealing. By observing very distant and therefore very ancient galaxies, astronomers can study conditions when the universe was much younger. The first galaxies formed a few 100 million years after the Big Bang, when the universe was less than 1 billion years old. These early galaxies were small and irregular, nothing like the majestic spirals we see nearby today. The James Webb Space Telescope has detected some of these ancient systems, revealing that star formation began earlier and proceeded more vigorously than many models predicted. This challenges our understanding of how rapidly structure formed in the early universe and suggests that the first stars might have been more massive and shorter-lived than previously thought. The expansion also affects our ability to study the cosmic microwave background in detail. This radiation has been traveling through space since about 380,000 years after the Big Bang, when the universe cooled enough for neutral atoms to form and photons to travel freely. The cosmic microwave background carries detailed information about conditions at that epoch, encoded in tiny temperature variations across the sky. These variations are only about 1 part in 100,000, but they reveal crucial information about the universe's composition, geometry, and initial conditions. As the universe continues to expand, this radiation continues to redshift and cool. Eventually, it will become so faint that detecting it requires increasingly sensitive instruments. The expanding universe is slowly erasing this crucial evidence of its own history. Another profound aspect revealed by expansion is cosmic time. Because different observers experience time differently, depending on their motion and gravitational environment, there is no single universal clock. However, we can define cosmic time as the time experienced by an observer who is at rest with respect to the cosmic microwave background. Such an observer sees the universe expanding uniformly around them, with no peculiar motion. Cosmic time provides a natural way to measure the universe's age and evolution. When we say the universe is 13.8 billion years old, we mean that 13.8 billion years of cosmic time have elapsed since the Big Bang for observers at rest, with respect to the expanding fabric of space. The expansion demonstrates how intimately space and time are linked. In general relativity, space and time form a unified four-dimensional structure called space-time. The expansion of the universe is not just space getting bigger, but space-time itself evolving. This means that the past is not just far away in time, but also represented by regions of space that were once much closer together. The future is not just later in time, but also regions of space that will be much farther apart. Time and distance become interchangeable concepts when dealing with cosmic scales, connected through the expansion rate. What makes the current epoch special is that we can still observe a wide range of cosmic history. The most distant galaxies we can see existed when the universe was only a few 100 million years old. Nearby galaxies show us the universe as it appears today, 13.8 billion years after the Big Bang. This range allows us to study how galaxies, stars, and other structures have evolved over most of cosmic history. Future civilizations will not have this privilege. As the universe continues to expand and accelerate, the observable portion of cosmic history will shrink. Distant galaxies will fade from view as their light becomes too redshifted to detect. Eventually, only the local merged galaxy will remain visible, and with it, much of the evidence for cosmic evolution will vanish. The expanding universe also reveals information about the ultimate fate of everything. As expansion continues and accelerates, the universe will become increasingly cold, dark, and empty. Stars will eventually exhaust their fuel. No new stars will form once existing gas is depleted or dispersed. The universe will enter what cosmologists call the degenerate era, dominated by stellar remnants like white dwarfs, neutron stars, and black holes. Even these will not last forever. Given enough time, quantum effects might allow even the most stable remnants to decay. Black holes will evaporate through Hawking radiation, a quantum process that allows them to slowly lose mass over immense timescales. The largest black holes will take approximately 10 to the power of 100 years to evaporate completely. After the black holes evaporate, the universe will consist primarily of a thin soup of elementary particles and radiation, all separated by vast distances and continuing to expand. This final state, sometimes called the heat death, represents maximum entropy. No gradients exist to drive any processes. No work can be done. No complexity can emerge or persist. The universe reaches thermodynamic equilibrium, a state from which nothing interesting can ever happen again. This fate seems inevitable, given our current understanding of dark energy and cosmic expansion. Unless dark energy behaves differently than we think, or some unknown physical process intervenes, the universe is headed toward eternal, ever-accelerating expansion into infinite cold and emptiness. Yet even this bleak picture contains elements of beauty and meaning. The expanding universe has created the conditions for complexity to emerge. The expansion allowed the universe to cool from its initial hot, dense state, enabling atoms to form, then molecules, then stars, planets, and eventually life. Without expansion, the universe would have remained a featureless hot plasma. The expansion provided the time and space for interesting structure to develop. While that structure is temporary on cosmic timescales, it is nonetheless real and meaningful during the epochs when it exists. We are part of that temporary structure, brief manifestations of the universe's capacity to organize itself into forms capable of understanding and appreciating their own existence. The study of cosmic expansion has transformed from curiosity to necessity over the past century. Edwin Hubble's initial observations in the 1920s showed that galaxies are receding, establishing that the universe is dynamic rather than static. Subsequent observations have refined our understanding of how fast this expansion occurs and how it has changed over time. Modern surveys involving millions of galaxies, sophisticated space telescopes, and precise measurements of the cosmic microwave background have given us a detailed picture of cosmic evolution from the Big Bang to the present day. What we see is a universe that has expanded from an incredibly hot, dense state into the vast, cold cosmos we inhabit, and which will continue expanding and cooling indefinitely. This expansion story connects intimately with fundamental physics. The relationship between gravity and expansion, between matter and energy, between space and time, all emerge from Einstein's general theory of relativity. This theory describes how matter and energy curve space-time, and how that curvature affects the motion of matter and energy. On cosmic scales, the equations of general relativity become cosmological equations describing how the entire universe expands or contracts based on its total energy content. Solving these equations with the observed energy content leads to the expanding universe models that match our observations so precisely. The expanding universe ultimately shows us that change is the fundamental nature of reality. Nothing in the cosmos is static or permanent. Everything is in motion, evolving, transforming. Galaxies form and merge and eventually fade away. Stars are born and die. Even space itself changes, growing larger with each passing moment. This cosmic impermanence applies not just to distant astronomical objects, but to everything, including ourselves. We exist as temporary patterns in an evolving cosmos, here for a brief moment before the universe moves on to new configurations. Understanding this does not diminish the meaning or value of existence, but rather places it in proper cosmic context, allowing us to appreciate the remarkable fact that the universe has organized itself in such a way that portions of it can think, wonder, and seek to understand the whole. The measurements that reveal this expansion come from multiple independent sources, each providing confirmation of the same basic picture. When astronomers measure distances to galaxies using Cepheid variable stars and compare those distances to the galaxy's recession velocities measured from redshift, they find a linear relationship. The farther away a galaxy is, the faster it recedes. This relationship, first quantified by Edwin Hubble, provides direct evidence that space itself is expanding. If galaxies were simply moving through static space, we would not see such a systematic relationship between distance and velocity. The pattern only makes sense if the space between galaxies is growing uniformly everywhere. Another source of evidence comes from the cosmic microwave background itself. The temperature of this radiation, currently about 2.7 degrees above absolute zero, represents the cooled remnant of the Big Bang's intense heat. As the universe expands, this radiation cools predictably. We can calculate what temperature it should have based on the expansion rate and the universe's age, and the measured temperature matches predictions precisely. This agreement provides independent confirmation that the universe has been expanding and cooling for approximately 13.8 billion years. The abundances of light elements also support the expansion model. In the first few minutes after the Big Bang, when the universe was hot and dense enough for nuclear fusion to occur, hydrogen fused into helium and trace amounts of other light elements. The precise ratios of these elements depend on the expansion rate during those crucial early minutes. Observations of ancient stars and gas clouds show element abundances that match predictions from expansion models almost perfectly. Hydrogen makes up about 75% of normal matter by mass, helium about 25%, and heavier elements only a tiny fraction. These ratios emerged naturally from the hot, dense conditions of the early expanding universe. The large-scale structure of the universe provides yet another confirmation. Computer simulations that start with the tiny density variations observed in the cosmic microwave background and evolve them forward through billions of years of expansion and gravitational collapse, produce structures remarkably similar to what we actually observe. The cosmic web of filaments and voids, the sizes and masses of galaxy clusters, the typical separations between galaxies, all emerge naturally from expansion models. This agreement between theory and observation gives us confidence that we understand not just that the universe is expanding, but also how that expansion has shaped everything we see. What makes the expansion particularly elegant is how it connects microscopic quantum physics with cosmic scale structure. Those tiny temperature variations in the cosmic microwave background, only 1 part in 100,000, originated as quantum fluctuations in the very early universe. During the inflationary epoch, quantum uncertainty in the energy density of space was stretched to cosmic scales. These quantum perturbations eventually grew through gravitational amplification to become the galaxies and galaxy clusters we observe today. The expanding universe has thus preserved and amplified quantum mechanical effects to astronomical proportions, creating a direct link between the smallest and largest scales of nature. The expansion also affects how we think about cosmic horizons. The observable universe, the region from which light has had time to reach us since the Big Bang, extends about 46 billion light-years in all directions. This distance is larger than 13.8 billion light-years because space has been expanding while light traveled toward us. A photon emitted from a distant galaxy 13 billion years ago has been traveling for 13 billion years, but that galaxy has moved much farther away during that time due to expansion. The actual distance to that galaxy now is considerably greater than 13 billion light-years. This means the observable universe is much larger than simple calculations based on light travel time might suggest. Beyond the observable universe lies the unobservable universe, regions so far away that light from them has not yet had time to reach us. We do not know how large this unobservable region is. It might be only slightly larger than the observable portion, or it might be infinitely large. The expansion effectively creates a horizon beyond which we cannot see, not because light is not traveling toward us, but because it simply has not had time to arrive yet. As time passes, this horizon expands, and previously unobservable regions come into view. However, this growth is now being offset by acceleration. The cosmic event horizon, the boundary beyond which galaxies are receding faster than light, is actually shrinking. Some regions that are currently observable will eventually pass beyond this horizon and fade from view. The interplay between these different horizons creates a fascinating cosmic dynamic. The observable universe is growing as light from more distant regions reaches us, but the reachable universe is shrinking as acceleration pushes more galaxies beyond the cosmic event horizon. We live in a transitional epoch where we can still observe a substantial fraction of cosmic history, but where an increasing portion of the universe is becoming causally disconnected from us. Future observers will have access to less information about the cosmos than we do now. Past observers, living when the universe was younger and smaller, could see less than we can. This creates a temporal window of maximum observability centered roughly on our current epoch. The expansion has philosophical implications as well as scientific ones. It challenges notions of permanence and stability. It shows that even the largest structures in existence are temporary and changing. It reveals that the universe has a history, a narrative arc from the Big Bang through the present toward an increasingly cold and empty future. This historical perspective is relatively new in human thought. For most of human history, the universe appeared eternal and unchanging. Only in the 20th century did we discover that the cosmos has a beginning, a middle, and an end. This discovery has transformed our understanding of our place in nature. The expansion also raises questions about what lies beyond the observable universe, and whether our universe is the only one. Some versions of inflation theory suggest that different regions of space might have inflated by different amounts, or stopped inflating at different times. This could create a multiverse of disconnected cosmic bubbles, each potentially with different physical properties. Our observable universe would be just one small patch within a much larger structure. The expansion that separates galaxies within our universe would also separate these different cosmic regions, making them forever inaccessible to observation. These ideas remain speculative, but they emerge naturally from mathematical models of the early universe and cosmic expansion. Looking at the expansion from a mathematical perspective reveals beautiful symmetries and deep principles. The equations governing cosmic expansion are surprisingly simple, considering the complexity of the phenomena they describe. This simplicity arises from the high degree of symmetry in the universe on large scales. The cosmos appears roughly the same in all directions and at all locations, a property called homogeneity and isotropy. This symmetry reduces the complex equations of general relativity to much simpler forms that describe only how the scale of space changes with time. All the richness of cosmic evolution, from the Big Bang to the formation of galaxies and the acceleration of expansion, follows from these elegant mathematical descriptions. The expansion ultimately shows us a universe that is comprehensible yet mysterious, ordered yet evolving, vast yet finite in its observable extent. It demonstrates that scientific understanding does not diminish wonder, but rather deepens it by revealing layers of complexity and beauty invisible to casual observation. Every measurement of cosmic expansion, every observation of distant galaxies, every detection of the cosmic microwave background adds to our understanding while simultaneously revealing new questions. The expanding universe presents an ongoing challenge to human curiosity and ingenuity, inviting us to probe deeper, measure more precisely, and think more creatively about the nature of existence itself.